Let's talk logarithms. And first, the basic concept of what a logarithm is. We have on this page a couple of number lines going vertical. And I'm going to use that to explain what the numbers mean. But first, a basic idea graphically of what a logarithm is. We were working before with exponential functions, which go like this, because that's something like, say, 2 to the x power. And that x changes and makes it go up fast and really fast as the x gets larger, because it's like 2 squared is 4, 2 cubed is 8, but 2 to the 4th is 16, 2 to the 5th is 32, so it goes up very fast. There is the inverse line of y equals x, that if we take the inverse of a logarithmic, the inverse of an exponential function, we get a logarithmic function. So these are exponential, and this is logarithmic. So we're going to be doing something different with the exponents here. Okay, so the basic concept of a logarithm. Okay, so I want to get most of this in, so I have to make this page a little smaller to show it. Okay, so I want to do a couple of numbers here. First, 10 can be seen as 10 to the first power. We don't usually show the 1, but the 1 is there. Let's look at where 10 to the second power is. That's here. That's 10 to the second power. So let's look at both of these. Oh, and then down to the number 1 here. I'll put 1 now. And that's 10 to the 0 power, because anything to the power of 0 is automatically 1. Well, here is what this becomes if I change it to logarithms. I'm going to change these three to a logarithm, and that'll help you to see where the exponent is. Okay, so we'll do, this one is almost easier to recognize. Log base 10 of the number 100 is equal to the exponent. Oops, we want that to go away there. It's equal to the exponent that it takes. So we have 10 raised to the power of 2. So this is the base 10 raised to the power of 2. So it's like it comes over to here. And I guess I'll use blue for this 100, because we know that 100 equals 10 squared. Well, we can write that 10 squared as log base 10, meaning that's the number that's being raised to the power. And log base 10 of 100 is equal to 2. And that 2, I'll use the red for it, that 2 is the exponent. So let's just come down here and write the same thing with this. So 10 is equal to 10 to the first power, which can be written as log base 10 of 10 is equal to the number 1. And here, log base 10 of 1 is equal to 0. Okay, oops, no, why am I doing 0? Yeah, oh yeah, 10 to the 0 is equal to 1. This one is a little harder to like really recognize, because we just don't usually use the 0 and 1s that way so much. But it's still true because it's following this pattern. So it's following having the base number here, the exponent number here, and what they're equal to here. So this is the base number, the exponent, and then what they're equal to. The base number, the exponent, and what they're equal to. Now I'll actually put base, exponent, equals. Okay, base, exponent, equals. Base, exponent, equals. Well, so far what you have seen, and I'll put this in black, is that the exponent with integers, we have 0, we have 1, and we have 2. I'm going to go to the number 50. 50 is equal to 10 to some power. And that's what we're now going to look at seeing. Here is where 1 is, and here is where 2 is. In fact, I'll do the 1. There's 1, and then 2 is way up here. So this one is somewhere in the middle, which means that it's going to have a power here of a decimal. It's going to be somewhere between the number 1 and 2. So I'm going to write this as log base 10 of 50 equals. Now, and this is something you can put in the calculator. If you put in that into a calculator, you're going to get approximately, so I'm going to change that to approximately 1.8451. And this is a good place now for me to mention that logarithms are always written to 4 decimal places. Always written to 4 decimal places. 1.8451. You are not allowed to round it after the tens, hundreds, thousands, 10,000th place. So you have to go out to the 10,000th place. Have to. Well, I guess you don't have to if you want to lose points on tests. But if you don't want to lose points on tests, don't round. Like this, some people would round this to 1.8 or 1.85 or 1.845. All of those would be incorrect. The exponent is 1.8451, or the log of base 10 of 50 is approximately 1.8451, and there is no other answer to give. So major lesson. Okay, must go for decimal places. You might not like it, but that's the way it is. Okay. So I'm going to make it really clear that that is a requirement. All right. So now that's understood. But my purpose of this mainly was to see that you can have an exponent with a decimal. And you can have, well, here's an interesting thing. 50 is not even halfway between the number 10 and 100, and yet it's at 1.8. Oh, no. Oops. Excuse me. I put the wrong number. Change that. Because the reason is because that's what 70 is. I was looking at the wrong paper to prepare, and that's 1.8451. So I meant to write it up here with this one. Let me write it more clearly. 1.8451, whereas the other one down here is a little smaller than that. But this will actually help to illustrate a certain point about this. This is 1.6990, 1.6990. You might say that 0 is not necessary. I want you to write it anyway. I want you to write 4 decimal places. Because if the number after that 0 had been an 8 or a 9 or a 7, it would have rounded it to 0. Clearly, the number after the 0 is less than 5. And so keeping the 0 identifies that. So always go to the 4th decimal place. Now here, this one can be written as log base 10 of 70 is equal to 1.8451. So I'm going to look at this number. If I can't, don't erase it on me. Notice that from 10 to 100, the exact middle point between 10 and 100 would be about 55, because that's what, 45, from 10 to 55 is 45, and from 55 to 100 is 45 places. You would think that this would be approximately 10 to the 1.5, halfway between them, but it's not. Okay, it's not that. Notice that the 1.699 is way low, or way higher than that. The reason it's higher than that is because this type of graph over here. So it's sort of like, now let's not go that way. Let's go only the other way. What happens, the graph goes up really fast and then it slows down. But by the time it gets like from here to here might be that 100. But what happens is by the time what we would consider halfway, well, the graph's gone up to that really fast. So the amount of x's it uses is actually, well, no, it's more the y's. So it's gone up really fast to get that way, and then it slows down. So it's just, notice it starts going this way, it's slower. It's not going up really fast anymore. It's sort of going a slower, it's going a slower up. Okay, now those arrows mess it up looking like it. So I'm going to erase those there because we don't need those to show the basic graph. Okay, so the logarithm is simply the exponent that gives you the integer number or another number between 0 and 100. So all the 1-point exponents are between 10 and 100. And if I went to 110 or 120 or 150 or 200 or 300 or 500, it would be 10 2-point something, 2-point whatever, until we got to 1,000, which is 10 to the third power. Then we get 3-point whatever up until we got up to 10,000. But notice there's bigger and bigger spaces between the numbers there. Okay. So now let's look at it with a much smaller one. Let's look at it with 2. That's why I have this other one over here. Still 4 decimal places. So the fact that that's written in there, I'll keep there. Okay. So all of these numbers here can be written as 2 to something. This can be written, well, not the 0. We'll do the other ones here. 2, 2, 2, 2, 2, 2, 2. We know that this is 2 to the 0, which makes a 1. We know this is 2 to the first power because that's just 2. This one is 2 squared. And then way up here, we have 2 to the third. So a very small space between these, a much bigger space between these, and a much bigger space between these here. Oh, come on, get in. I'm not going to keep those there, though, because I want to illustrate these other numbers. This one, the 3 is going to be 2-point something. It's going to actually be 1.5850. Now, 3 is exactly halfway between 2 and 4, but the exponent is beyond halfway. So it goes up faster and then starts slowing down before it hits 2. The same thing here. If I go to the number 6, that's 2.5850. For base 2, 0.5850 is the middle of each of them. If I went to 2 to the 4th, then the number 12 would have 3.5850. And then if I went to 2 to the 5th, which is 32, I think we'd be looking at 24. At 24, we'd be at 4.5850. We can also fill in these other ones. So this one is 2.3219. And 7 is 2.874. You do this on the calculator. Now, and here's an interesting thing. I'm doing it with the calculator. You're going to have to practice this. And there's a point to practice that. First, on the calculator, you have a log key on most calculators. That is base 10 only. Okay, so that's an important recognition. That's base 10 only. Now, I'm going to check it. If you want a different base, okay, I'm going to be looking using the TI-84 series. And for that, you press a math button. Press the math button. And then you look for, let me find the right log number. You do math, and then you go to the B, no, it's A, okay, A, scroll down, okay, and the A is called log base. Actually, this is in capitals there. And it puts a parentheses. And what it'll do, okay, it will show you this once you press it. Log, a little box for the base number, and a big base, a big thing for the number that you're looking at. So for instance, if I did, I'm going to come over here for space. Let's actually check out this one of 3. Log base 2 of 3. Okay, and it gives 1 point, that's approximate because it never stops, 1.584962501, and we want to go to this place. Well, the 6 rounds the 9 to a 10, and then that means we add 1 to the 4 to make it 5. That's why we have the number 1.5850, because the 49, because of the 6, rounds up to 50. Okay, and that's what you can do if you have the TI-84 series. Okay, there is another way to do it if you have a calculator that doesn't have this command or this one, and I'll show you that in a moment. Okay, let's move here. I already mentioned about the graph of the different functions. I should have moved to this page, but that's a better drawing than me. But I am going to simply write exponential and logarithmic. They are inverses. Okay. Now, types of logarithms. Logarithms, like what we've been talking about already, where A is the base. And I do mention here about about that 84 newer. Common logarithms are where it's base 10. Okay, we don't show the 10, so that's why notice here we would do log base A of B, and here's just log B. It's understood that that's a 10, that the base is a 10. And so you can just use the log command on the calculator. Natural logs is a slightly different thing. It's log base E of whatever number, but we write it instead as natural log. Okay, so it comes up with different numbers than the log numbers. So you can't use, that's why there's an ln one on most calculators. And most of the time it's the second function for log, but not always. So you have to look carefully at whatever calculator you're using. And it might be under the math key in some cases. Okay, and I told you 4 decimal places. Okay. This is the thing you use if you have a calculator that doesn't allow you to put a base number on the bottom. Notice this, that the base A, get log B over base A, over log A. So it's sort of like this gets a log and this gets its own log. So they both get a logarithm. And that means they're both log 10s. So log base 4 of 17 is log base 10 of 17, and log base 10 of 4 And so with the base 10, you can just use the log key on any calculator. You divide those and you get this number, 2.0437. So know this. Okay. Know this. Okay, then you have to write it out that way. The domain of a logarithmic function. So one of the things to point out here is that, well, in fact, come back and look at something with me for a moment. Look at this graph. Notice the current domain of it. This going down here, we are going down to negative infinity, but we're going over as we keep going over, we're getting over to 0 from the positive side, and then it stops. So it never is going to cross that. That line's an asymptote. That means the x's going that way never go less than 0. Never go past 0. So the domain is starting from 0 and not including it and going to positive infinity, because this is going to go forever that way. But going if you were to go towards the left, you get closer and closer to 0 but never touch it. That means that they can't be negatives. All these negative x's are not part of a logarithmic function. So when we come down here, that means that this thing, whatever it is, cannot be less than or equal to 0. So you do that the domain is 3x plus 6 must be greater than 0. Not equal to, but must be greater than. So subtract 6, 3x is greater than negative 6. Divide by 3, x is greater than negative 2. So all the numbers in the number line larger than negative 2 will work. Because if I put negative 2 in here, I get negative 6 plus 6, I get a 0. You can't have log of 0. Doesn't matter what the base number is, you just can't have 0. So, however, log is greater than negative 2. Let's take negative 1. Negative 1 is greater than negative 2. So if I put negative 1 in here for the x, I get negative 3. 6 take away 3. So we'd have a positive number in there. So that's perfectly acceptable. So what you want to remember is to do this kind of thing. So the domain is going from negative 2 to infinity. Okay. Now, here are some little rules about logarithms that you need to know of. So if this number is 1, that means you get a 0 here. Doesn't matter what the base is. Base does not matter. If these two are the same, it's 1 automatically. Automatic. Same thing here. If these two are the same, then whatever this exponent is becomes the answer automatically. That's just a rule. Just memorize the rule. By the way, these two are the same, and that's because this has a 1 exponent. We just don't show the 1. So you can think of it that way. Now, here is an interesting one. We have an exponent that has the log in it, but because these two are the same, the base number in the exponent and the main base number out here, because those two are the same, that means that the y is the answer automatically. Now, over here, in fact, for each one of these, we now have numbers for them. Okay. So this, no matter what the base is, if it's to 1, it's 0. That's because if I rewrite this, I get 7 to the 0 is equal to 1. And what I just did there is I switched around between a logarithmic equation to an exponential equation. This is the one where if these two are the same, then it's automatically 1. Here, if these two are the same, or a logarithm that is, then that means that the exponent is automatically the result, that the whole mass is equal to 4. And here, if the big base number raised to a power has logarithmic log of that base as in the power, then that's automatically the exponent there, or the number that you would get as to find the logarithm is the answer to it. Okay, now, and what this illustrates, I'm going to change each of them to exponential functions. So this one can't be as easily. So either of those, I won't actually do that with either of those. So let's practice a couple of these things. In fact, this might be good now that you look right now at this. If you think you understand these, pause the video, do them, and then come back. And I will pick it up right now, but you will have paused it and come back already by the time I start doing these. All right, let's take a look at this. The domain, I have to make this greater than 0. So I'll do 4x plus 26 is greater than 0. And if I subtract 26 from both sides, I get that 4x is greater than negative 26. Divide by 4, x is greater than, well, 4 goes into 24 6 times, the other 2 is 6.5. Okay, so that means that the domain is going from negative 6.5 to infinity. So you can have a negative exponent, like let's say, or a negative x, as long as the whole thing in here does not be negative. So if I put negative 5, which is in this range here, I put negative 5 in here, let's say, to check it, that gives me negative 20 plus 26, that gives me a positive 6 in there, and as long as it's positive, it's a legal thing to do. You can do it. Okay. So I'm going to put base 10 there, and then make it so it's readable, though. Enlarge this to put the base 10. So I'm going to evaluate that. What I really have is that this is log base 10. Another way to write the number 1,000 is to write it to 10 to the third power. And that means it's automatically equal to 3 because of this double 10 thing. Now here there's a 2. Oops. That's going to be equal to log base 2. You have to recognize now that it's possible that these numbers could be a number that's that's another number to an exponent. And that means this one's equal to 3. In this one, because of these two, that's just simply equal to 17. And here, if these two are the same, because there's really an exponent of 1 there, that means we have 1. Do these. So there's a beginning introduction about logarithms. First, what they actually mean, that they are the exponents to have, so that you can have a base number, and any single number on the number line can be rewritten with that base number raised to a decimal exponent. Then we have the fact that these two are inverses, and then the basic types of logarithms, so that these numbers, these terms need to be recognizable. You want to know what they mean and how to use them. 4 decimal places. Definitely the change of base formula is helpful, and you must know that. And recognize that for the domain, you have to make sure that what's inside is has to be greater than 0. Okay, so that's why automatically you have to make sure you do that. Right. And then here there are these particular, like, you want to recognize that rule, that rule, that rule, and this rule. Because you'll see them just like we did down here. Here were some of those different rules being used. So that's a good introduction. I hope it helps to understand it. Thank you for watching and listening.